Welcome to BCN Analytics. We will talk about causality. Bartek Skrzydlski will talk about AB testing, and I will talk about causal inference. I'm Aleix with Evilla, by the way. We hope you enjoy it.
Wow, full house. Good evening, everyone. Welcome to this new BCN Analytics session. For those of you tweeting or using social networks, the hashtag we are going to use today is BCN Causality, because we are going to talk about causality. Question, who is the first time joining our BCN Analytics events? Raise your hands the ones. Wow, many of you, or most of you. So just to give you some context, in BCN Analytics, in the previous sessions, we have organized several events like this. We've been talking about the usual suspects, right? Machine learning, deep learning, artificial intelligence. You remember when you were no one in the city if you were not talking about machine learning, so we were also there talking about all these topics. We felt excitement about machine learning, don't get me wrong, deep learning, artificial intelligence. But in one of the last sessions, it was the first time that we raised one of the, let's say, the flip side of machine learning sometimes is these black box algorithms. And we had a nice conversation about the implications in terms of bias and in terms of discrimination, so the ethical dimension of machine learning. Today, we want to even broaden the scope, and we want to talk about the why. Some of us are really on existentialism, right? So we don't want just the data, we want the answers, the why, the reason why, the reason why. And also we remember this famous, I think it's one of the first concepts you get in statistics, right? That correlation does not imply causation. And here we took from this famous website this chart. Not sure how many can you see it, but the black line is the number of movies done by Nicolas Cage. He used to be a great actor, you remember, living in Las Vegas. I don't know what happened to him, but we are not going to talk about Nicolas Cage. In this chart, you see in the black line Nicolas Cage movies, and the red line is number of people who drown by falling into a pool, right? So this is a perfect example of the problem of correlation and not being causation, because obviously, as far as I know, there's no relationship between the movies of Nicolas Cage and people falling into a pool. In fact, when we were researching about this concept, I was really happy to see that companies such as Uber, in this case, are already investing resources in causal inference to improve the customer experience, right? So this topic is not just a few of us thinking about why. It's becoming a hot issue in the industry. Also, Aleix, who is one of the speakers today, shared with me this article where you could see that understanding what causes disease is also becoming one of the areas of application of this approach. So from our side, causality is a very relevant and broad topic. And we wanted to go deep about this topic, so we say instead of having just one session to talk about causality, we believe we're required to do it in a thorough way. So we are organizing 2 events. This is the first one, the part 1, and right after Christmas, we will organize a second event to follow up on these topics, because we believe only one session wouldn't be enough to really capture the potential of the topic. Also recognizing that this is an effort that we are doing from BCN Analytics in combination with Machine Learning Meetup group. In fact, we have here 2 of the representatives, Aleix and Bartek. So they are going to be leading this session. Before getting into that, in the whole session, we also have one person in the team, in the BCN Analytics team, Didac Fortune, who is also participating in a cool initiative, Data for Good. So I'm going to ask Didac, I cannot see you, are you here? Okay, to talk a little bit. So an spontaneous applause to Didac, please.
Hello?
Funciona.
Hi, before starting the talks, let me summarize in 2 minutes what we do at Data for Good Barcelona. We are an initiative that wants to encourage the usage of data and the exploitation of data and analytics for social purposes. So for the reason, our target we are focused on 2 targets. First, NGOs and other social projects that can make use of their data. And the other target is data professionals who want to volunteer and dedicate their spare time to help others doing what they do at work, mainly data science and other data-related things. If you want to know more about this, here you have links to our social media, the Twitter account, our own webpage, and even better, if you subscribe to our newsletter. In the newsletter, we share the events that we organize. We organize about one meetup each quarter, and also we share information about other initiatives related with data and related with social good that happens around Barcelona. So again, if you want to know more about it, just contact us or contact me or other data for gooders that are in the audience, and we can talk more about this. Thank you.
I use this one. Thank you. Getting there. So just before getting into the topic, big thanks to our sponsors. One of them is Adevinta, the company behind Habitaclia, Milanuncios, Coches.net, Fotocasa, Vivo, Motos.net, and InfoJobs. Thanks to Adevinta, we are recording this session, so if you want to enjoy the content later on in our YouTube channel, we will upload the whole content. Also, big thanks to Movistar Centre. They are sharing with us this venue, this great venue. So big thanks Movistar, and also big thanks to Estrella Damm. I know some of you come for the beers, so after the talks there are some beers and also water for those not drinking. So they are going to be over there. So big thanks to Estrella. So to summarize what we are going to see in the next minutes, we will have a panel. It's going to be Bartek and Aleix. And for the first time, instead of having one presenter and then the other one, they decided to do a joint presentation, both of them at the same time. So we are innovating in the format. So they will be together spending around 45 minutes talking about the topic. They built a nice presentation. Then, as usual, we have an open session for Q&A. I really encourage you to participate, because maybe we don't address all the questions today, but it's good to know what is interesting. So the next session on causal inference, the part 2, is really shaped along your question, right? So make sure you ask questions. And then we have, as many times in life, trade-off. So you could ask as many questions as you want. However, if you want beers at 8:25, we need to move there, right? So I believe in democracy, so if some people want to be like drinking beers, that's fine. If some people want to get more questions, or we could get the questions in the beer. So around 8:20, I will say, hey guys, we are 10 minutes ahead. You want to stay here with the questions, or you want to follow up the questions there in that side of the room? Because at 9 sharp, the place will be closed and we will have to leave the building, right? So with that said, I'm gonna ask both Aleix and Bartek to come here to the stage and present. You guys want me to read your bio, or you want to present yourselves? I mean, I could read.
We can present ourselves.
You can present ourselves? You have that ability? Yeah, fine.
I don't know. That's right.
Yes. So let me see. Good.
Or you want him to write?
No, you can.
Then, perhaps, so big applause for the two guys who are presenting. Thank you.
Okay, thank you for coming. I'm Aleix Ruiz de Villa. I studied maths and I did a PhD in maths. I worked in some transportation company, very nice company here in Barcelona for some years, and then I started to be a data scientist. I worked in La Vanguardia, in Lidl, as a SCRM, which is like a startup from Lidl, and ONA, which is a startup here in Barcelona. We also organize this meetup machine learning with other colleagues from a long time ago, maybe 2014, and yeah, basically that's that.
I'm Bartek. I work in Alpha. It's a startup or moonshot made by Telefonica. We are working together in SSRM for some time, and I was working also in King and in Shipstead, which is now Adevinta. And yeah, we are going to talk about causality. So let's start, and I will start with the difficult question: who likes pizza? Yeah, I know, but who believes that pizza can reduce risk of cancer? Definitely everyone who raises hands would like to know it, right? I definitely would like to know. If I knew that a pizza reduces risk of cancer, it would be a great news for us, right? So actually there's this article by Italian, surprise, surprise, scientist, and they actually studied if the pizza can protect us against cancer. So what they did, they collect information from patients of the different kind of cancers, and they ask them questionnaire about 78 products, about their daily use of this, how they consume this product. On the other hand, in the another patients with a different diseases or problems, they ask the same questions, the same questionnaire about 78 products. And what they find out that among this 78 product, pizza was the one that actually has a p-value pretty low. And so it seems that pizza, it's a good candidate for saving us from cancer. It's a good news, right? But there is of course a problem. I would love to that if it's true. It would help me a lot. But even they are saying this kind of things that they are not clear that this conclusion and the pizza is they could really move this and to other population, not Italian. So is it? And this is actually what you already heard, that this is kind of things that we are talking about, that pizza can protect from cancer. This is like a direct thing, and direction is cancer. But what they are doing is actually correlation. So, and this is what is the talk about. We're just trying tells you more or less how you can, on one hand, save you from this kind of potential mistakes, and how you can eventually do something useful.
The talk, it's a little bit large, but the main things that we want to transmit you and we would like you to take out home, it's these 3 points that we want to highlight. The first thing is that we really want causality, but we usually talk about correlations, and there's a gap between this. And the first thing is to acknowledge that, okay, I'm interested in causality. I do the best I can because there are lots of limitations, but causality is the objective. The second one is that causality is hard. It can be highly misleading. You can take very wrong conclusions with very easy problems, and we will see that after. And in fact, this is affecting the first one. Sometimes it's so hard that you say, okay, let's say I only having correlations, because saying that here there is a causation, it's really hard. Okay. And the third one is that for dealing with causality, the solution is to approach. It's A/B test or randomized control trials, when you can make experiments, and when you cannot make experiments, then you have to go to causal inference. So these are the 3 main relevant points that we would like you to have a clear understanding on this.
Yeah. So especially the first one, we already started that. We are saying that we would like to really causality. This is all what we need. So let me start from something. There was everyone probably heard that, and we are hearing all the time that there is this big data promise. That big data promise that all you need is to collect lots of data. You collect lots of data, and once you have this huge amount of data, you will be able to deliver a lots of business value. So probably many of us face this kind of situation that our companies invest lots of money in big data infrastructure. This is where we start. However, there is a small problem with that. And so we have all this data, and then what next? So probably very often one of the solutions we propose is a dashboards. Let's produce lots of dashboards, and so we kind of have this very sophisticated tools with 100, 200 dashboard that we feel like we're sitting in the cockpit of the space shuttle, that we are seeing all of everything what happens around us, and we just, if there is a problem, we can just steer out with the steer wheel, or just press some lever to stop something when something goes wrong. Unfortunately, it's not like that, because we really see the correlations. We really see on this dashboard correlation, although we have many different correlations, that probably this lots of dashboards is, first of all, it's complicated to follow. And the second one, correlation are like this. Probably, who knows this example with the chocolate and Nobel Prize? Probably it's a very famous example, shows that, another interesting example like pizza, shows that if you put the countries here, on the line. And you see how many chocolate people consume in this country per person, and how many Nobel Prize they have per person. We see clear correlation that here, that more chocolate people consume, more Nobel Prize they have, which is another interesting insight from this talk. After pizza and chocolate, if this is true, then probably we could, education of our kids would be much easier. We just give them pizza, which is good for cancer, and chocolate to make them more intelligent. Yeah, but of course, we know that unfortunately, correlation is not causation, and this way of correlation, of doing correlation, and it's a way to just hit the rocks, and.
Okay, let's talk a little bit about what's the problem with causality. Okay, how many of you know Simpson's paradox? Many of you know, because I know that you know. But okay, since Simpson's paradox, it's we will see it's a very well-known example that taking a decision, it's not straightforward. It's not trivial. This is real data, and there are many examples with real data. In some hospital, they wanted to cure the kidney stones. They had stones on the kidney, and they had two treatments, A and B. Okay, and they made an experiment. They gave treatment A to 350 people and treatment B to the same amount of people, and then they saw that 83% of the people taking the treatment B recovered, and 78 of treatment A recovered. So the first conclusion is treatment B is better. Okay, this seems kind of straightforward. Of course, it wouldn't be a paradox if it were that easy. Some days later, they realized that they also had this information about the stones that they were dealing with, the size of the stones, whether they were large or small. So they thought, okay, let's include it in our analysis. We have this data here. Let's put it on the analysis and see what happens. And what they got is that for the large stones, 93% of the people recovered with treatment A, which meaning that treatment A was better. And with the small stones, also treatment A was better. Okay, so maybe you're starting to feel like what? Okay, so if the hospital has to stick to one treatment, which one should they take? Okay, this is the main question to this problem, and it's not easy, and arguing which is the solution is what we are going to do. Okay, so far, how many people think that A is the best one? Okay, and B, which you think it's the B, it's the best one? Okay, yeah. So so there's now we're starting to go into the causal inference realm, and there are two ways of dealing causal inference. One is called potential outcomes, and another one with graphs. We are only going to talk about graphs. Okay. So if we wanted to describe this situation in the hospital with a graph, which one we should take? In this one, we have like each arrow. It means for us a causal relationship. Okay. In this one, we have the size affecting the treatment, and the treatment, the recovery, and so on. And in this one, we have the other way around. Okay, so there's one of the two that describes best the situation of the hospital, who thinks that the one on the right is the best one, and the one on the B. Okay, so the B is describing this situation, because we will see that the size of the stone, it's affecting the treatment. Why? Because it turned out that when the patient came into the doctor's office, the doctor made a guess to try to see how large was the size. And treatment A, in fact, was doing surgery. So they opened people and they took out the stones. And treatment B was taking a pill. So they wouldn't give treatment A to people that had small stones. Treatment A was mostly for the difficult ones. So the size of the stone was altering the probability of having one of the two treatments. Okay? Which could be the situation? This situation could be different. This situation could be the one that if you take the treatment, after that your kidney expands or reduces. Okay? This is the other situation. In causality language, we say that the size here is a confounder because it includes confusion to us. We don't know how much the treatment is affecting the recovery or how much it's the stones, the size of the stone affecting the recovery. Okay? And on the other hand, in the other situation, the size somehow it's part of the dynamics of the treatment. Here, if you give one treatment or the other, you don't really care how it's going to affect the recovery because it has like many paths. But what you want to know is how this affects to this. This doesn't make you a confusion. It's part of the process. Okay, so here we're modeling the situation with these two different graphs. And if we go to the data and see the distribution of stones, we saw that actually treatment A was getting 75% of the large stones. The large were the ones that were more difficult. And treatment B got the other way around, 75% the small ones. So it's a totally unfair comparison. Treatment A could be better, but if it's having the difficult situations, the performance could go down. Okay? So this example, it's one of many examples of having observational data. This happens when you are not running an experiment. These data were given to them. It's like this big data scenario that you go to a company and they say, oh, hey, you have these lots of data, analyze it. This is observational data. It's data that you haven't been there to make a proper experiment to get this data. Okay? And this Simpson's paradox, it's one among many, and you can imagine there are more of them. Okay? And it's quite striking. So the solution comes from these two methods. If you are able to run an experiment that you can define how you're going to get the data, the best is to run an experiment. Okay? And this is A/B testing. If you have the data but it was given to you, then you are analyzing data with causal inference techniques. Okay? But there are only these two scenarios. Either you can define the experiment or either you don't. Okay?
Yeah, so let me do some small review what is A/B testing. So do you know which century was the first A/B testing executed or control randomized trial? Do you know? Who knows? So actually it's interesting because first effective one was done in 18th century by James Lind. So at that time, scurvy was a disease affected especially people in the sea, on the British ships. That people we know now that the scurvy is caused by lack of vitamin C, but at the moment it was totally unknown. So this guy have this idea that okay, I will go to the trip. Some people will get sick. The sick people I will split into few groups. I will start to feed them with different food and see which food actually is better for them. Actually, he has a kind of idea that probably there is some kind of special elixir that he can make out of fruits that it could help them. So obviously, not surprisingly for us anymore, that the citric food was the one that people that were eating them, they get better. Which was very good experiment, very effective one with a perfect result, doing randomization, But surprisingly, it didn't work very well because, as I told you, James Lind has this idea that now he will just make these fruits, boil them, and create a liquid, and will give to the people that. So of course, we know that boiling fruits kills vitamin C. So this experiment was forgotten for some time, and after 50 years later, it was again the treatment was rediscovered. But nowadays, this controlled trial, randomized trials or AB tests are very popular. Not only in the medicine, where most of the new medicines are going through very well-defined and controlled by authorities experiments, but also in most of the companies that are new companies use them. Not only for learning, not only for testing things, but the most importantly, to build product. So they build product for experimentation. A/B testing it's an easy idea. It's just, as we are discussing, just let's have two groups of people, and one group of people give one product or one version of the product, the other group of people give another version of the product, and then see which one is better. Idea is simple, but unfortunately, very often and too often, very poorly executed. And on the other hand, it's not always possible to run the A/B test. And so let me talk about these two cases. First of all, pitfalls with the A/B test. So again, A/B test, which is carefully executed, it's an excellent tool for finding causality. But, for example, typical pitfalls. So first one, which is very common, as I saying, let's split people and see which one is better. But there's no really clear hypothesis. What does it mean to be better? So experiment is run, and then what? I don't know which one is better because there's no clear, for example, in which situation better, and how we measure, which means better. So it's very, very important to define what is our way of the measuring, what the better means. And this is also extremely related, this not clear hypothesis, to the second thing, which is a cherry picking of results. When we do not know, when we do not define upfront what we would like to test, then we can lead to this kind of funny comic one. Probably many of you knows that. So they run experiment testing if jelly beans is linked to acne, and they did randomized trial and then see there's no any relation. But then they started to look at the different colors of these jelly beans, and finally they find out that the green one is the one that has 95% confidence that it works. So this is very similar, in my opinion, to the pizza thing, that it was 78 product, and out of this we are find out that pizza is one of this, something like this green jelly bean situation. And another one is also related to this, is we are doing too many groups. And so when you do many groups, then again, it's very similar to just cherry pick the group that works. So again, both cases, if we really would like to do this kind of things, we have to do much careful statistics. We really need to taking in account not only if we do statistics and do confidence interval, not only this particular groups, but we need to also take into account the calculation that we have many groups here. So it's confidence has to be much higher, because basically if we throw a coin sufficiently many times, it's something. Then at some point we get 5 heads. So this is kind of similar to this one. Another example, and this is also very heavy, is we don't do any group size estimation before running experiments. So we're just running experiment, we are observing and hoping for the best, or even worse, at the moment that we get some kind of significance in any way calculated, we just stop it. This is also this kind of stopping is related to cherry picking. We're just waiting for the moment that is good, best for us. And so again, if we are not well prepared and we are not make sort of sure, which is something which is called power analysis, that we have enough users to, in reasonable time, have a reasonable result, and then we are facing this kind of problems and getting to results that are not reproducible in later. Another one, it's also happened in the pizza, probably, not clear randomization. Very often we are not randomized. We're just saying, okay, we are just test a product during 1 week and other version of product during another week, and we compare it. But what could happen is just, for example, the other product, the second product was tested in the first week of December when actually there is higher sales because people start to buy Christmas present, and we can get to conclusion that version B is better than A. Or maybe in this pizza, maybe people that will actually get cancer, they actually didn't eat pizza because they actually were feeling bad long time before getting cancer, or whatever can happen. I don't know. So this is, and another one. This is also very, very, very popular, which I see many times. That okay, we are run experiment. We don't have a significance difference. Then we can assume there's no difference. So it's perfect. But it's like trying to look at the stars through the glasses. You just don't have a proper tools to observe stars, and maybe the effect is, maybe it's important. You just do something that you just was not able to observe. So it's like a very typical, few of them typical pitfalls. One I've seen many times, and there are more. There are more. So, but I wanted to say here that it's important to run the A/B test in the sort of rigorous way. It's not just, and we will get back to this at the end. So the second point I wanted to mention is we are not always able to run A/B test. So, for example, limitation. It can be impossible to run A/B test. For example, we would like to see how the product of a competitive company is affecting us. We are not able to just test two competitors' product, for example. Or running A/B test can be timely or costly. If we, for example, have an education platform and we would like to develop a product that in the long term people would get better scores in the university, but actually the product you need many years to really learn, let's say, mathematics, and so this could be costly to test, and very often it can be unethical, especially in the area of health, when you cannot, for example, test if the smoking causes diseases. You cannot just a group of 15 years girls or boys randomly divide them and ask them to smoke during 30 years and then see if they get worse or not. And also, it can be complicated to run many experiments at the same time. So because they can kind of, first of all, you maybe not have enough users for that. If you want to, they separate totally. And if you start to cross A/B test running at the same time, they can infer with each other on lowering or doing uplift of the non-existing results. And so now let's go. In this situation, what we can do? In this situation, we can try to look at the causal inference.
Yes, as Bartek said, this should be clear that if you can run an A/B test, do it. Causal inference is when you cannot do an A/B test, okay? Because with A/B tests, as we will see, you don't have the problems with observational data. However, it's not always possible to run an A/B test. So the first idea I want to explain to you, it's the philosophy behind causal inference. Think for a moment, in the case of the kidney stones, if we were beforehand and we could run an A/B test, afterwards we would like to draw a graph of the dynamics of the A/B test. Okay, so we've seen before two graphs on the kidney stones example, and now I'm asking you, if I run an A/B test, which graph would I have? Any ideas how the graph would look like in this case? So here we have two graphs corresponding to two different situations. This one was the one we were dealing with, and this one, the treatment affected the size. But if I had run an A/B test, what would the graph look like? Any ideas? So it would look something like this. Well, not something like this. It would look like this. The size, it's not affecting the treatment anymore. The treatment that you are having is totally independent of the size of the stone. This is the randomization breaks this arrow, and this is the most important thing in A/B test. When you run an A/B test, you're cutting the dependency with other possible confounders. You don't have confounders, and that's why your conclusions are clear. Okay. So this is what would like a graph from an A/B test. But this is the data we have. The data we have has been generated with this type of dynamics. So the philosophy behind causal inference is, okay, this is what I have, and this is what I want. I would like to have data generated by these dynamics. And can I find a way to go from here to here? Okay, and this is the essence of causal inference. Can I do something with this information that resembles what would I have taken if I had done an A/B test? Okay, and the answer is yes, depending on the graph. Okay, and if you do this thing with the Simpson's paradox, you get that the A is better. Okay, what is it? I'm not going into details, but what is the idea of this maths arrow that it's here? It's the following. This is the distribution that I had, but if I had run an A/B test, my distribution would like something like this. So can I rebalance my treatments in a way that it's weighted with this information? Okay, this is like the technical. I'm not going into details, but this is the technical answer that it's behind this arrow here. Okay, so the idea of causal inference is try to mimic an A/B test. First question: is this always possible? We will get an answer, but no, it's not always possible. So far, what tries to solve causal inference? The first thing that tries to solve causal inference, it's a side effect, but it's very nice. It's state clearly what I want to measure. Okay? Imagine this situation. You have a newspaper. I worked in La Vanguardia and for some time. So imagine you work at a newspaper. You have a newspaper. That would be nicer. And you have two types of news: culture news and sports news. And you also usually make ads of them. You take some news and you post them on Facebook or on Google or whatever. And the dynamics would be described something like this. Imagine, for instance, that during August you got more culture news, but you also used more Facebook ads because there was a promotion of Facebook ads. And then it comes September and the sports season starts, and then you got more news about sports, and then also there's a bonus on your Google ads and whatever. So it may happen that some topics have been used more in some platform and some topics on the other. This is a very natural situation that can happen in many companies. So my first question that I would like to know is, okay, which is the interest on the topic on its own? Okay, I cannot go and just look for how many visits did the culture news got, because this is affected from the platform. Maybe the platform was more effective, or people from one platform liked more this kind of news. So the first question is, which is the topic effectiveness? And this is this arrow here, okay? So I can, with the graph, I can plot it very nicely. And my second question, it's the other way around. Which of the two platforms work better? If I had to stick to one of those, which one should I take? And if you see, it's the same diagram as before. In this case, the topic, it's a confounder. It's something that affects the platform and also the visits. Okay, so it's the same situation as we saw on the Simpsons paradox. So you are prone to have a Simpsons paradox here. The second thing that tries to solve is helping you with the confounders. Why? Because having these variables that affect both, you are never sure you are not missing one of them. So the method doesn't tell you what you are missing, but imagine the following situation. Imagine the situation that you know that the topic is really relevant, but by some reason you don't have this information. Maybe because an intern dropped the database, or maybe a senior, probably a senior, dropped the database, and you don't have this information, but you know that this information it's important. Causal inference tells you, okay, in this situation, what can I do? And in this particular situation, you cannot do nothing. You cannot make causal inference. Whatever thing that you are trying to estimate with this arrow, it's affected by this, and you cannot make this difference. So the answer in this situation is do nothing, or run an AB test, or get more information, okay? But makes an assessment, or tries to make an assessment of the risk of having a confounder. And the last idea is life is complex, okay? And reality is complex, and your daily work may look something like this, not a 3 nodes diagram. This is an example from this book, Inference and Intervention, and in this example, it's running something, a hospital, but it could be a company. You have many variables that are of your interest, for instance, your brand image, or your costs, or your profit, and it's very natural to ask how my brand image is affecting my profit, or my cost is affecting my profit, or my brand image is affecting my cost, or all these kinds of questions, okay? So think for a moment. If with the 3-node diagram we have so much difficulty, how many Simpsons paradox and selection bias and all the things that you want can be hidden here? It's like a danger game. It's very difficult to deal with. So with causal inference, what tells you is, assuming this is the graph, then you can do these mechanics, these formulas, you can make these calculations, and in these cases you are doing well, and in these cases you are doing wrong. Okay, so this is a third thing that causal inference solves. Okay, so from these examples, we can see some things that our intuition has told us for many years, but somehow this is the proof of it. For instance, data doesn't speak by itself. Okay, this is total fantasy. It's totally wrong. Okay, here with 8 numbers, which were the Simpsons paradox, we needed to model the process in order to solve it. We need a model for 8 numbers. It's kind of crazy. Second thing, more data doesn't solve the problem. Okay, in causality, it's not always a problem of data. In machine learning, mostly it is, depending on the scenarios. Okay, but mostly it's a problem of having more data. But in causality, it's not enough with more data. Which variables do you take into account in your analysis? It's really relevant and can make you have biased conclusions or unbiased conclusions. And as we saw in Simpson's paradox, having bias, it's not the idea of, okay, this is the true value and my bias is like this. No, in Simpson's paradox, it's like treatment A or treatment B. Okay, it's the totally opposed conclusion that can make you go wrong. Correlation is not enough. Correlation, it's symmetric. Correlation between A and B, it's the same as B and A. And causality, it's not. So you need a language that includes directionality. Otherwise, you're missing something important. Different models lead to different conclusions. And this is a responsibility for us as humans, that we make models and we take consequences of those models. Okay, here and understanding what's going on, it's really relevant. And this is totally different from machine learning. In machine learning, there's a typical scenario that I give you data and you run a machine learning model and you get like 99% of precision, but you didn't understood anything at all. Okay, this doesn't work for causality. You need to understand the domain knowledge. And at the beginning, this is bad, but for the humans, it's good, because automating machine learning, it's kind of easy, but automating causality, it's much, much, much harder. And on the other hand, you have to work with the departments. You need to work with humans to really understand the process. And humans in this case are really, really crucial. Graphs are a very nice tool to understand things. Probably you have realized, maybe not, but I have been in some situations that people having zero technical background whatsoever, and I showing them like typical scatter plot, and do you see it? And they say yes, but no, you're not seeing nothing. And I show them a graph, and oh, there's an arrow missing. It's like, okay, but I haven't still showed you yet the graph, and it's pretty natural for humans to think in terms of graphs. So if you have insights and you want to share them in form of graphs, that's a very nice thing to have. And the other thing that when you do causal inference, you have to never forget, it's about confounding variables. Confounding variables, you always may have confounding variables and can really affect your analysis. Okay, so to start finishing, some conclusions. These conclusions are kind of shared between the two techniques. The first one is that with one experiment or one analysis, you don't get clear conclusions. It's more like this cycle that first you do a hypothesis, then you do an experiment or you run some calculations about causal inference, then you take conclusions, and from these conclusions, then you think about other hypotheses. And it's the loop itself that brings you the knowledge. It's not just one experiment that gives you everything.
Yeah, so we can maybe, and it's very important as we are discussing, to have some kind of rigorous here. So hypothesis in both cases, we have to choose carefully, and we have to know how we are measuring if the hypothesis is true or not. This is first thing. Then, and there's another thing that very often, especially in it's forgotten, but it's important that, okay, we run this experiment, we do this analysis, what we do next. We are not just, especially in the context of the business context, we are not just running experiment just for the sake of experiments. Like we are discussing, this is very often a very powerful tool to the product development. And so if we get experiment, if we do this causal inference and we get results that we hypothesize, what we'll do next? What would means for us? This is kind of a product decision. Then kind of what we are discussing before, you can go one or two to arrow, you can go with A/B testing or causal inference. As Aleix was already saying probably 3 times or 4, that the moment that you can, the moment that you have a possibility to run A/B testing, do this. It's not just causal inference. It's not just a tool that you can do equally plug-in instead of A/B testing, but has some advantage, as we were discussing before, especially in the situation when you cannot run A/B testing, or you have lots of different hypotheses, and you would like to look at them. And then after all, as always, you have to look if your results are just by chance or statistically significant. This is important. And at the end, out of it, you get some insight, what you have learned, what are questions, next questions, what are the most important things that you don't know, and then go over and start again.
And yeah, just to finalize, about this Uber platform that Manuel said, they have a very nice blog explaining many things that they run with causal inference, but I'm choosing this one, which is a nice one. Uber has drivers, and these drivers have an app, and from time to time they have problems, and they send tickets to Uber to solve these problems. Among these problems, they have one particular area, which is their own earnings. Okay, and usually Uber just puts a number with the total amount that you have earned this month. But at some point they wanted to understand whether putting a graph there with the evolution in time of your tickets decrease the number of tickets. Okay. So what they did is they run an A/B test. They design an A/B test and they run an A/B test. They took 2 groups, one showing them the graph and the other one showing not the graph. Okay, and they saw that the graph helped to reduce the number of tickets. But there were many reasons why people stopped sending tickets. And they also wanted to know how much this graph helped people to understand, to have an understanding, or a better understanding of their earnings. So they sent a quiz, a rating about 1 to 5 stars, about how well did they understood the graph, how well they understood their earnings, and this was for everyone. This was not an A/B test. And in this case, they draw this graph. The earnings, the experiment help you to understand your earnings, and this decreases the support. So their question is, among all the things that decrease my tickets, how much is due to my understanding of the tool? Okay, so this is a causal inference problem because they didn't run an A/B test for that. They run an A/B test for another thing, but they use this A/B test for complement it with a causal inference technique. So there are many situations, in fact, that causal inference and A/B testing can work together, and that's also why we wanted to organize this talk in this way. Okay, yeah. And finally, you can find in this blog all this diagram telling all these are different techniques, causal inference techniques, and in each case which one you should use. So it's something that they run many times and they have good knowledge of it. Okay, so again, the 3 main points, just to be clear. In fact, what you are really interested in is in causality, not correlation. The second one is be careful with causality because it's hard, can be highly misleading. And the third one is that the solution is both an A/B test and causal inference. Okay, that's all, and thank you. Hope you enjoyed that.
Thank you.
So now time for questions. So we will jump into you guys instead of us asking questions. So bring the chairs and then we can start with the questions.
Merci.
Sure.
This is for what?
No. Okay.
Hello. Hello. Thank you very much for your presentations. Really nice, really hot topic and very relevant. So my question is an overall question related to the process you suggest us to follow to assess the causality. What should be the process we should perform to start taking into account the issues of the causality, these graphs? So how should we perform this? I think it's a question for you, Alish.
Okay, in causal inference, how do you, what's the process, the working process?
Yeah.
The working process is first think about all the variables that you think that may be relevant to your analysis and list them all of them. The second thing is build a graph out of it, and the graph is really relevant. The graph is going to condition your analysis. And the third thing, when you have the graph, make assessments whether the data that you have is enough or not. And probably the fourth one is make the calculations. Of course, you have to define what you want to calculate inside the graph. Okay, I don't know if this answers you a little bit. There's a question.
Thank you for the talk. So in relation to that question, do you have like some insights on what is the maximum number of variables that you could model using causal inference? Because you mentioned it's quite complex, like the graph becomes really complex and you have to understand well the relationships between the features, let's say. Do you like have any practical guidelines in terms of like a manageable number of relationships that you could handle in a graph? And like what is you mentioned also like this, you have to know the size basically of data. So what is the relationship between, and you also mentioned that like the more is not necessarily better, like what is the minimum number of data points you need, for instance, to be able to properly model causal inference?
The question is about the maximum size of the graph and then the data. How many data do you need? Okay, the first thing, the graph can be as large as you want, because there's a nice property that you don't need all the information on the graph. There are some, let's say, theorems, algorithms, whatever, that tells you, with this graph, if I want to calculate the effect of this variable into this variable, you have to take this variable, and this one, and forget about the others. So the size of the graph, it's not a problem. In fact, the larger, probably better, because you have more understanding on your problem. Once you do that, this follows in the technical part. Whatever machine learning technique that you have, you can apply it. With causal inference, then you have to modify it somehow. Okay, the somehow it's the key. But let's say that the same confidence intervals that you have with the statistical techniques are similar to the ones that you can use in causal inference. Okay? Does this answer the question? Okay.
More questions?
Do you know of any methods for discovering the causality graph?
Okay, discovering causality in graphs, it's hard. If causality is hard, discovering causality in graphs, it's even harder. There are two answers to this. Okay, the formal and the human. The formal, it's for many causal models, you may have the same data distribution. Which means if you have data, you cannot invert the process to find the causal graph, okay? In general. On some types of graphs, you can grasp some information, okay? This is the mathematical intuition. The human intuition tells you, in fact, we haven't been running experiments for so long. As humans, we have learned lots of things, and we daily understand more things. from observational data. We don't run A/B tests for everything. So probably there's something we can do with the data itself to help us to recover the graph. Okay? And there was a very nice talk about Bernard Sholkov in CCCB last week. And he has a group that precisely tries to address this problem. When can I recover the data from the graph from the data? Okay, but it's a very open problem.
You've shown us an application of causality in the analysis of experimental results. But can I also use causality in modeling my data for applications in industry like this? So not just for the analysis of the experimentation, but to compete, for example, with a deep learning model or something like this.
Okay, can you repeat again the question?
Can I use causality also in modeling my data to do inference for an application in industry?
Okay, so, but the question is, what's the difference between causality and deep learning somehow?
That's one way to take it, sure.
Okay. Okay, imagine, I'm going to try to explain in different steps. Imagine that you want to make a model. You are a machine learning engineer, okay? And you want to make a model to predict cancer. You go, you take the data, and you have this model, and then when someone comes, you make a prediction of how confident you think that this person is going to have cancer, okay? This is a prediction that you have a system, and you are not altering the system. In machine learning, you predict things as far as you don't interact with them. The main assumption in machine learning is that the things are identically distributed, okay? The other part, that it's what statisticians and medical doctors have been doing for ages, is I want to build a model to understand which factor produces cancer. Because I'm not going to evaluate this model for each new patient. I want to understand why. So, as far as your application in your company requires your intervention, you should be interested in causality. For instance, recommender systems. Recommender systems, there's a nice situation. We work together with the recommender systems at Lidl, and we run a recommender, and the most recommended item was the plastic bag or something like that. And the second one was bread. Okay? And why is that? Because the usual way of dealing with recommender systems is trying to predict what is going to be most probable. So this guy is going to buy bread. It doesn't depend whether I recommend him or her or not. Okay? What happens when you have a large e-commerce? People are not aware of the items themselves. So if you show them, then you are making an impact. But in other scenarios where people know all the items, then that implication of a recommender system, it's not so straightforward. So, for instance, recommender systems. If you run recommender systems, you would like to understand the treatment effect of your recommender system, whether I'm making a recommendation makes an impact or not. Pricing. If you're doing prices, if you're doing pricing, you should be interested in that because the price that you put alters the dynamics of the system. So there are hybrid situations where you would need both at the same time, but those are the most difficult situations regarding machine learning. But in general insights, you can draw a map of whatever. So it's directly applied. So
great, thanks.
Okay. 8:20, time for one more question.
This is your chance, yeah?
Does the idea of representing these causal relationships by a graph, is this always sufficient? Can you also express interaction between variables, like things that it's not clear, it's not immediate cause and effect, like between one variable and another, but involves higher order interactions.
Okay. When you draw a map, a graph, you are drawing the relationship, like the relationships, but you are not telling which kind of relationship is there. Meaning, yes, you can put whatever statistical model in the graph. So you relate which is the relationship with a variable and its parents. So there you can apply whatever statistical deep learning, machine learning model that you want. So if there are like interactions among them and you're using a polynomial, for instance, there's no problem with that. I don't know if I've answered the question, but the answer is you can use any functional that you want on that.
Okay, so thank you very much. Again, so a couple of things, beers, water over there, so you can ask more questions to the two guys. And also, since we are thinking about the second session, please throw us a message either now or through Twitter or through email so we get some feedback on what would be interesting, because we are thinking about the second session and we want to make it useful to you guys. So please share your interest with us, okay? So thank you, big applause for the guys.